Okay, two very important examples of subspaces. Null space first. We'll define that. So we will let A be a m by n matrix. Then the null space of A. Some textbooks will put another L in here. I don't like to because can't teach an old dog new tricks. But be aware that there may be an extra L in here. Null space of A. Now, null, referring to the zero vector. So it is the vectors in Rn that are killed by A. Well, that's, when multiplied by A, they become 0. So the null is referring to this 0 here. So null space. So how do you find null space? Well, you typically have to solve this system here, right? We've solved these homogeneous systems many, many times. Exercise, I would like you to show that null A is a subspace of Rn. Okay, you are not going to need to know anything specific about A other than that it's a m by n matrix. So I want you to try this exercise. If you're having trouble, please ask me in class. I'll be more than happy to walk you through it. Next we have another definition. This is same setup. Let A be m by n. Matrix, of course. The column space of A, call A. Is different than the null space, of course. It's going to be the set of all these guys, where the vector x can be anything in Rn. So it's the set of all products Ax. So x can vary. X has an infinity of choices. And we collect all those things in a bag, and we call that bag the column space of A. So this is the column space of A. And this is the null space of A. Okay, once again I will ask you, as an exercise, show that this is a subspace of Rn. Okay, pause, copy, try that. Pause, copy, try that. Pause, copy, try that. Here's my solution. So the column space. So it's all vectors of this form. Okay. Is a 0 vector in there? Well, what is in here? It's anything of this form where x has to be in Rn. Well, I can choose x to be the 0 vector. So I can write like this. I can go 0 is equal to A times 0, right? Right? And then this guy is of the right form. So this call A is a bit different, right? It's given, not like null A. Null A is given as a condition that you have to satisfy. Call A is given differently. It's given as a form that the elements take. So good thing to keep in mind. So all I need to do to show something that something is in call A, I have to show that it equals A times some vector. That's all I need to do. Easy peasy. So that's what I've done. Okay, this is clear. So boom, that is in call A. Check mark. Good job. All right. Do you agree? Reading this from left to right, do you agree or disagree? Hopefully you agree. But if you don't agree, come talk to me. We will talk you into it. Now, if I have two things in call A, so let AX1 and AX2 be in call A. Okay, how did I know to write them down like that? Well, I don't have a choice. I have the elements of call A have a very specific form. Okay, if I'm choosing two elements at random in call A, they both must be of this form. That is what call A is. It is what it is, bro. Now when I add them, if I add them, what happens? But what do I want to do here? What do I want to do? I want to show that this is in call A. How do I do that? Well, I show that it's of this form. I can write it as A times a vector. Well, easy peasy. Factor easy. Factor out that A. So now I've shown that the sum is A times a vector. So my reader can see that this is clearly in call A. Three, let K be a real number, and let AX be in call A. K times AX. I want to prove that that's in call A. Well, look at this. Look at this. You have the arithmetic of the matrix vector product. It says that this is the same as this. Okay, this happens a lot, it seems, in this course. You have a real number here, got a matrix vector product here. You can move that K around pretty much as you wish. And there you have it. I have taken my scalar multiple and I've written it as A times a vector. So this is in call A. Okay, that's how you determine if something is in call A. Is it or is it not a matrix times a vector? And this certainly is. Okay, there we go. 1, 2, 3 in the bag.